Hi everyone, and welcome to this video on the investment opportunity set, as well as the minimum variance set, which is part of our module on the modern portfolio theory. So in the last video, we discussed the portfolio diversification effect, and we said that it's a good way to bring down the overall portfolio variance and reduce the risk of the portfolio. And that is, we want to ensure that the idiosyncratic risks are kept to a minimum, while the only risk that may remain would be the market risk. And one way to do that is to be able to diversify the portfolio. So let's now tackle this concept called the investment opportunity set and the minimum variance set. So given the values of the variances and the correlation coefficient, we are able to determine the portfolio's expected return and variance for different combinations of various portfolio weights. So you could have an equally weighted portfolio or an unbalanced portfolio, one wherein a security may be higher in its weight than another asset inside of the portfolio. And when you plot them in the mean variance space, we obtain the graph known as the investment opportunity set of the two risky assets. Now, for the case of only two risky assets, the investment opportunity set is also the minimum variance set. And essentially, the minimum variance set is the locus of expected return. So it's the collection of expected return and risk combinations offered by portfolios of risky assets that yields the minimum variance for an expected rate of return. So, so we have that sort of concept if you connect all the portfolios with varying weights. Now, a subset of that minimum variance set is what you refer to as the efficient frontier. Okay, so this is the efficient frontier. And the efficient frontier is the set of portfolios that offers the highest expected return for a given variance. So for example, for a two risky asset portfolio, assuming that the return on one is higher than the return on two, so asset one's expected return is higher than asset two's expected return, but the risk or the standard deviation of asset one is also greater than asset two, then the MVS, or the minimum variance set, is the curve that connects points A and B and represents the risk and return trade-off as X2 increases and thus X1 decreases. So it's going to be some connecting curve that we have there. Okay, so that's going to be a representation of the MVS. So that's the MVS. Okay, so the MVS formed by two risky assets, well, it depends on the magnitude and sign of the correlation coefficient of the returns of the two assets. So you let X1 be the portfolio weight of asset 1 and X2 be the portfolio weight of asset 2. And you have a couple of cases. In fact, you have three cases on how this thing will look like. The first case is if you have a perfect positive correlation. So that's rho 1, 2 is equal to positive 1. And that's rare, of course. So when the two returns of the assets move in exactly the same direction or are perfectly positively correlated, then we observe that the MVS is a linear and upward sloping curve, right? So in fact, if you take the derivative of the expected return with respect to the variance, then you get this exact thing here, right? And the slope is greater than 0, right? So again, if we're just gonna make it this one, okay, this that's just the difference in the returns minus the difference in the standard deviation. That's gonna be the slope of the MVS. The slope is greater than 0, right? And is a constant and is independent of the level of X1. Note that X1 is not in the computation at all. And as these cases are holding, okay, so the slope is a slope that's greater than 0, independent of X1, and a constant. And thus, the curve connecting points A and B is an upward sloping straight line. So that's actually the one I drew earlier was an example of case 1, or your perfect positive correlation. So you have just a straight line connecting the 2 points. Now, a more interesting case, at least for us, is a perfect negative correlation. And as we said in the portfolio diversification effect, this is sort of an ideal scenario wherein you have asset classes expected returns moving in likely the same in opposite direction, such that when one is affected, the other one is not that affected. So when the two returns of the assets are perfectly negatively correlated, then the relationship between the portfolio expected return and standard deviation can be given by the line in the next slide. Now, with a perfect inverse correlation, then it is possible for us to construct what we refer to as a perfect hedge. So it's possible for us to form that sort of um, hedge. And it just means that the appropriate choice of the portfolio weight of asset one will result in a portfolio of the two risky assets with zero variance, a very rare case, right? And it looks something like this. So ACB is now going to be our curve that we have. So we have ACB. So that line there will be what we have. And that's in case two. So how did we get to that? So if you recall, when the correlation coefficient is perfectly negative, it's equal to -1. And if you recall, if we have that case, then it should mean that the standard deviation has both a positive and a negative root, right? And the MVS, or the minimum variance set, is given by the line ACB, is actually really two line segments. So if you recall, you have sort of this one segment and then this other segment, right? You have two there. And one of them has a positive slope and one has a negative slope. So AC is a positive slope, and then you have CB has a negative slope, right? And what we can do is we can demonstrate that the signs of the slope of these two line segments are determined actually by this standard deviation formula. And they intersect with the vertical axis at the point wherein the MVP has a zero variance. Okay, so it's easy to show. First, if you recall, the X1 under the minimum variance portfolio has this formula. So the quote unquote optimal portfolio weight under a minimum variance portfolio for X1 has this formula. But in a perfectly negative case, we can substitute that and we can yield this sort of form there. Therefore, 1 minus this one, which is X1, is just equal to X2. So we're left with this one being X1 MVP, then this one being X2 MVP, right? So we have those two things. Now, if we substitute that into the equations of portfolio expected return and standard deviation, we can get this one, which is the overall portfolio return or expected return. Now, something interesting happens when we substitute these weights to the portfolio standard deviation equation. So if you recall, this is your standard deviation equation. If you plug in X1 and then 1 minus X1, that's just X2, okay? You get this one, which is equal to 0, right? And that's an interesting case, right? Thus, the MVP of the two risky assets is generally a portfolio with a positive expected return, but with zero risk, right? And this is given by the point C in the graph that we've had. Now, let's examine the properties of the line segments. As I said, you have generally two line segments there. One that is positively sloped, which is your AC, and one that is negatively sloped, which is your CB. Note that for a portfolio with perfect negative correlation, the standard deviation has two roots. You have a positive root and a negative root. And now, since the standard deviation cannot be negative, the two roots of the standard deviation must be interpreted as follows. So, as long as what you choose as X1 is greater than the X1 in an MVP, then you are under the positive root. But if your X1 is less than your X1 MVP, then you are at your negative root. And essentially, the two results just imply that AC and CB are linear cases, right? So we see similar results to case one, albeit with slightly different things. So effectively, you see approximately the same slope if you derive it. That's mu1 minus mu2 over sigma1 minus sigma2. Both of that is greater than 0. But if you're now at CB, at line segment CB, remember that's a downward sloping line. If you take the derivative along that line, you are somewhere that is negative, right? So you see a negative slope. And this is true under this assumption. So when you plug these things in, you'll hold that this is greater than 0, this one is less than 0. And the efficient frontier of the minimum variance set for the case of a perfectly negative correlation, however, is only the set of the portfolios that lie along the upward segment, the upward sloping portion, which is AC. So again, as this one says, the EF, or the efficient frontier of the minimum variance set, is only the upward sloping portion of that curve. In essence, it just means that you shouldn't be choosing a portfolio with a higher variance at a lower expected return. So you essentially find the lowest variance, or the portfolio with the MVP, then look at its variance. Then if you look at the expected returns of that, the expected returns that are at a higher variance but give you a lower expected return should be taken out. And those all lie in the downward sloping portion. Only the portfolios would have a higher expected return and potentially a higher variance would exist in your EF. The rest would be strictly dominated, and you should not even consider those strategies because you could have a higher expected return at the MVP, which again yields the lowest risk. Okay, so that's the intuition behind that. Case 3 is our last case here, which is an imperfect correlation. So in general, any portfolio combination formed by two risky assets that are less than perfectly correlated, that is, you lie between the interval -1 and +1, must lie inside of the triangle ACB. So if you recall, this was the perfectly negative case. This was the perfectly positive case. So we now have the case wherein it's somewhere in the middle. So we have our MVS to be that set. Now, which is part of your efficient frontier? That would be this green one here. That's again the upward sloping portion of that curve. We'll get to know what this means through an actual example when we get to the next video, when we use two different stocks. So we'll use two different stocks and we'll construct their efficient frontiers. So thank you for your attention in this particular video, and I'll see you in the next one. Thank you very much.